So our next speaker is Jannis Limperg, who's going to tell us about Aesop and tactic optimization, I guess.
Thank you very much for the introduction. I'll talk about tactic script optimization for Aesop. And let me first demystify the last word in the title here. So Aesop is a tactic for customizable proof search in Lean 4. It's quite similar to Auto in ROC/COC, also similar to Auto in Isabelle, actually more similar to the Isabelle version, etc. So it applies user-specified rules to goals. If a rule doesn't fully solve a goal, the rule produces some sub-goals. Aesop is called recursively on the sub-goals until hopefully at some point there are no goals anymore. And the rules are really arbitrary tactics, although we provide some syntactic sugar to register particular theorems as rules. But under the hood, we're dealing with arbitrary tactics here. And all of this was presented 2 years ago by myself and Esther, who happens to have the next talk in this session. All right, so the topic of this talk will be tactic script generation. So here we have, as an example, some theorem that says that the head of the concatenation of two lists is the head of the first list, provided that the first list is not empty. And with a little bit of help from this rule that we add here, Aesop is able to solve this. And then we can use the variant Aesop question mark, which allows us to basically replace Aesop with an automatically generated script, right? And the script is essentially generated by Aesop taking the rules, turning them into tactics, which is relatively easy because an Aesop rule under the hood is very similar to a tactic, and then printing them to get this kind of script. However, if we do this naively, it doesn't look quite as nice as we have here on the right-hand side. It looks more like on the left-hand side. So it's a script that works and solves the goal, but is very, very ugly in a couple of ways. First of all, it's just a list of tactics with no structure, whereas here, we have these combinators like next that allow us to focus on particular goals and to say, okay, so for example, this subproof all pertains to the goal that we focused up here. And second, tactics are sometimes applied out of order. So this on goal 2 here means that we apply the tactic to the second goal in the current list of goals. That's quite unnatural when you write proofs as a human, right? You usually just want to attack the first goal until it's gone, and only then do you switch to the next goal. So it's a bit annoying. And there are all these simp-alls. I don't want to get into the details of why, but basically these simp-all calls, if you have them in the middle of a proof, are a big no-no in lean land because they are quite unpredictable. They depend on some global state. If the global state changes, the simp call does something different than before, your proof breaks, and you get unhappy. So therefore, in the middle of a proof, we prefer the simp-all only form, which essentially kind of removes the dependency on the global state. So that's an optimization that we would also like to make. Now, what I basically did in order to fix all these issues is to write a script optimizer. So a little program that takes the naive script, turns it into the optimized script. And this talk is going to be about how exactly I did this. But first, maybe a little bit of motivation or additional motivation about why we want to optimize. So here are a few use cases where this is useful. First, the most common use case is we might want to replace Aesop with the generated script for performance, right? Because Aesop does a bunch of search, it tries a lot of tactics, which may or may not take a while depending on how fast these tactics are. Sometimes they're quite slow. And so using the generated script, of course, cuts down on all the tactics that we tried during the search that didn't actually lead to a proof, so it can substantially increase the performance of the generated script. But here we want an optimized script because we don't want to, PR this kind of garbage here to Mathlib, because the Mathlib maintainers will shout at us that this is unacceptable. Then you can also let Aesop generate a proof stub. So even if Aesop doesn't manage to prove a goal, it can still usually make some progress using so-called safe rules, which are always good to apply. And then Aesop basically gives control back to you and says, okay, now let's prove the rest. But in that case, so if you use this methodology, you probably also want to replace Aesop with the generated proof stub. And finally, the scripts can help you learn about how Aesop proved a goal, either for debugging or, this is a kind of funny use case. So recently, a lean user, newish lean user, talked to me and said he had learned some lean by running Aesop on simple goals and looking at the scripts that it generated, which taught him about some of the kind of basic tactics that we use in lean to prove stuff. Not a use case I was anticipating, but I was quite happy to hear about this. Okay, and looking a little bit further into the future, script optimization is not only useful for Aesop, and in fact, the current implementation is only coupled very loosely to Aesop. It's also useful for AI, right? We're seeing a lot of these AI-based systems that generate tactic-based proofs, and these sometimes already contain some sort of post-processing that's quite similar to what I'm doing, because the proofs generated by these AIs usually tend to include a bunch of garbage that doesn't actually contribute anything, so they need to be post-processed in some ways. And thinking even further into the future, I think it would be nice if eventually we as humans could just write a proof in whatever kind of way we want, being kind of as dirty as we like, and have an optimizer clean up after us. This would bring us into the realm of sort of auto-formatting tools for programming languages, stuff like that. Okay, for now, let's kind of stay in the present and stay with what I actually implemented. So I implemented a script optimization pipeline with 3 steps, and I want to talk to you about the first 2 steps. The first step is what I call local dynamic optimization. This is where we take single tactics, that's why I call it local, and we optimize them, and then we check whether the optimized version actually behaves the same as the version that Aesop ran previously. This is an important check because, for example, for this simp-all optimization here, due to limitations of the lean API, / maybe it's also not possible to also always do this soundly, I'm not sure. The optimized version is usually correct in the sense that it behaves the same as the original version, but not always, so we need to check this. Then the second step is the most involved and does the structuring that I already talked about in the introduction, right? So it takes this script, which is just a list of tactics, and transforms it into this tree where we focus on specific goals. And it also does this reordering where these on-goal 2 things disappear if possible. And the third part of the pipeline is global static optimization, which I will not cover in this talk because it's not so interesting. Basically, it just does some very basic rewrites on the final script. These are purely syntactic. That's why I call them static. And they work on the whole script rather than on individual tactics. That's why I call them global. Right, before we get into this, a little note about the input of the optimizer, so what we get at the start of the pipeline. We get a so-called naive script, which is a list of script steps, and a script step contains the syntax of the tactic that Aesop ran, which can also be a tactic sequence because lean doesn't clearly distinguish between the 2 things. And in addition, it contains a pre-state, which is the state of lean, if you want, before the tactic was run by Aesop, and the goal on which the tactic was run, and a post-state, which is the state after the tactic was run, and the goals that it produced. This is very useful because it allows us to check whether a tactic that we optimized has actually the same behavior as the tactic that we had previously, which is the entire point of local dynamic optimization, which I'll get to now. So we've already looked at the example, and I've already explained the issue, right? The simp-all only thing is not always correct. So what do? Well, we check whether it is actually correct or not. This means that we generalize the script steps such that they can now contain multiple alternative tactic syntaxes. And we basically just try them kind of top to bottom. Right? So we first try the simp all only tactic, and we check whether if this tactic is run in the pre-state of the step, it produces the expected post-state. If it does so, great, we'll take this version. If it doesn't, we'll move on to the next tactic. And the last tactic in the sequence is always assumed to be a fallback, so it's always assumed to be correct in the sense I just mentioned, so that we have some form that we can use. Now, this is conceptually very easy, but there is one technical niggle that I wanted to talk about because I think it might be of more general interest than just this work. So to decide whether a tactic produced the expected post state, we need to compare whether the expected goals and the actual goals are equal. And there is a little problem with that, which is that essentially the internal names of hypothesis and also meta-variables, which I haven't mentioned yet, are unpredictable. So what that means is, suppose we have the simp all only thing and the simp all thing. We execute both with the exact same goal, and we get two goals that look exactly the same as well. So we would certainly want to consider these two tactics as having the same behavior. However, internally, the two goals that are produced use internal names for the hypothesis, which are unique names generated by some global name generator. So the actual names that Lean uses to identify these hypotheses are unique 1, unique 2, unique 3, and so on and so forth. And hence, the two goals are not equal, kind of on the nose. And with how the Lean API is structured, I don't think there is any reasonable way that we're going to convince Lean to give us exactly the same names in both cases, particularly when the two tactics here might be implemented differently. Okay, so what do we do? Well, we need to compare the goals up to renaming. And I imagine that I'm not the first to come up with this, but it was not clear to me when I did this work that this was the right notion of equality, so I wanted to quickly present it here. Basically, what we want to do is we want to go through the goal, starting with the first hypothesis here, and we compare the two hypotheses. So we compare the types. Types are list alpha on both sides. So we can consider these two hypotheses the same, and we store this fact in a map down here that we are going to carry around while we compare these two goals. Then we move on to the second set of hypotheses. Again, it's list alpha, again the same. We store this identification. And now for these hypotheses here, the types are not exactly the same on both sides, but we have already remembered that we want to consider unique 1 and unique 4 to be actually the same. So we consider them the same in this case as well, and we identify unique 3 and unique 6. And we continue with the target of the goal, which I've elided here. And we do a similar thing also with meta variables, where it's slightly more complicated. So this gives us kind of the right notion of equality for comparing goals produced by different tactics with potentially different names. All right, moving on to the second and most involved stage of the pipeline, which is the structuring stage. And here, the main problem, although there are a bunch of other problems that I also discuss in the paper, but the main problem is that Aesop may solve the goals in an unnatural order. The solution obviously is, okay, we want to reorder the tactic such that they are applied in the natural depth first order, right? So we always attack the first goal first. Here's again the example from the beginning. Right, we have these on-goal 2s, and we want to move these tactics to the place where they would naturally appear. Right? So this one gets moved 1 down, this one gets moved 2 down, because these happen to be the places in the script where these tactics would usually be applied. Now, this is all good and not very hard, but unfortunately, it becomes difficult when we have goals with meta variables. With the problem being that reordering is actually unsound in general when goals contain shared meta variables. And I'll demonstrate with an example here. So let's say we have this tactic state. We have two goals. The first goal says that meta variable n is less than 42. Second goal says meta variable n equals 0. And meta variables stand for arbitrary terms to be determined later. Right? So you can think of it as a typed whole in an expression. So down here is a script that works when we try to solve this goal. Right? So we first run the reflexivity tactic on the second goal here. What this does is it solves the equation or proves the equation by reflexivity. In order for it to do that, this question mark n must in fact be 0. So the tactic assigns the meta variable n to 0, and therefore all occurrences of meta variable n get replaced by 0. And the first goal therefore changes to 0 less than 42. Now we run the second tactic, which is decide, which runs a decision procedure for less than on concrete natural numbers. So it's able to solve this goal, no problem. Now, if we permute these two tactics or reorder them, they don't work anymore, because we tried the decide tactic first on the first goal, but there is nothing to decide here. We don't yet know what the left-hand side of this inequation is. Therefore, the decide tactic will fail, and we never get to the second tactic, which would have told us what this question mark n meta variable actually is. So we lose some information, essentially, and the reordering has made a script that previously succeeded fail. How do we deal with this? I actually propose two methods for dealing with this. So let's take this example. This is a very synthetic example. I apologize. There are more natural examples, but I was too lazy to find them. So we have one goal here, which is true, and there exists an x such that 1 equals x and x equals 1. And okay, there is the original script down here. And we want to reorder this as much as possible. And the idea here for static reordering is very simple, right? As long as we don't have meta variables in the tactic state, we don't have a problem. We can reorder at will. As soon as we have meta variables, we stop reordering. So that's the whole idea. So we start by applying kind of the most natural tactic. Right? Here there's only one goal, so we don't really have a choice anyway. We apply this and.intro. And now here there are two goals, but there are no meta variables inside, so we can reorder. So we take the next tactic that applies to the first goal here, which happens to be the third tactic, true.intro, in the original sequence. Okay, now again, we only have one goal, so we don't have a choice. So we apply this exists.intro, and here we have reordered, and that's fine because there was no meta variable. Okay, now we have a goal with meta variables. Now we need to become more careful, and becoming more careful basically just means, okay, we take the tactics from the original script in exactly the same order that they were applied there. So we get this and.intro, and then on the second goal we run refl, and on the first goal we run refl, and we get a partially ordered script. However, you might have noticed that in this case, if we go back to this state, it would have actually been fine to reorder the remaining two tactics as well, right? Because we just run refl on both goals, and it doesn't matter in which order we do that. And that's precisely the idea behind the other approach to reordering, which I call dynamic reordering. So here, the idea is when we're in the state, we try to reorder kind of optimistically, because even though reordering is unsound in general, it is sound in some cases. So we can just try it and apply this last refl tactic first, and then we happen to get a goal that is actually solved by the remaining tactic, so that's fine. Now, what if this tactic here hadn't succeeded? Well, basically then we reverse the reordering, right? So we backtrack and we try a different order, and then try the dynamic reordering algorithm again. This makes it exponential, which is a bit unfortunate. However, there is kind of a sanity check that we do after each reordering decision to make sure that, in this case, this refl tactic has approximately the behavior that we were expecting. The precise sense of this is discussed in the paper and also has to do with this kind of equality between goals algorithm. And this sanity check should, in practice, cut down on a lot of the kind of exponential or a lot of the choice points that make this algorithm exponential. And indeed, in the paper, there is an evaluation where I try this script generation functionality on all the 6,000 Aesop calls in MathLib. So I generate scripts for all of them. And it turns out that the dynamic reordering is slower because it does need to re-execute some tactics, but it is still kind of within acceptable bounds. Most dynamic reordering calls are still relatively fast. All right, so to conclude the talk, I've presented a 3-step pipeline for tactic script optimization. I focused in particular on 2 of the steps, which are local dynamic optimization and structuring with these 2 reordering algorithms I discussed. If you want to know many technical details, including precise descriptions of these algorithms and a lot of stuff about specific ways that lean represents hypothesis names and so on and so forth, you can read all of that. I hope you're happy that I spared you from this kind of stuff. And of course, as future work, I think many more optimizations could be added to this and should be added to this. For example, for the AI use case, it would be very nice to detect which tactic steps are actually required for the final proof, because the AIs tend to insert a bunch of steps that don't actually contribute anything to the proof. So that's an obvious optimization that could be added. And there are a lot more. I'm sure you can probably think of some as well. All right. That's all I had for you today. I was a bit quicker than I was expecting, so that means we have a lot of time for questions, and I hope you actually have some.
Thanks, very interesting. I was wondering, you talked a little bit about why reordering is unsound, and the example you gave was with these meta variables. And I think you said that it's unsound if there's overlap between the meta variables in these goals. But then you went on to explain that, well, my impression was that you basically just try to swap these things, and if it doesn't work, then you revert back, right? But isn't there like a more subtle way where you check if there is actually overlap between these meta variables before doing that?
Yes, great question. So indeed, the current implementation considers this goal here already kind of unsafe, even though we actually have only one goal. And if we had 2 goals here, where we have like a meta variable x in one goal, a meta variable y in one goal, the current implementation would also consider this unsafe, even though it is perfectly safe. The reason for that is technicalities. Basically, it's quite annoying to carry around a tactic state that accurately represents which meta variables occur in which goals, because the tactics that are executed can have an effect on the meta variables that appear in different goals, because they can assign a meta variable that appears in a different goal, and then you get basically changes in these meta variables. In order to track that precisely, one would have to do a lot of bookkeeping, which I didn't want to do because the static reordering algorithm is incomplete anyway. So I hope that this is not a big problem in practice. If it is a problem in practice, it could be fixed.
In the static reordering, most of the examples, so when you do on goal 2, it's more, then it can generate itself sub-goals. And is it easy to keep track on which goal the next tactic will refer to with respect to the original organization?
Yes.
The
so
bookkeeping stuff?
So the goals are all identified by unique names anyway in the original naive script, which makes it relatively easy to track which goal a script step refers to. The only thing that we need to do is when doing this when executing this algorithm, we need to keep track of a representation of the tactic state so that we know at which position at which position each goal that we are currently working on is located. That is necessary to generate these on-goal 2 thingies, for example, here. And yeah, this is a bit annoying. It's also connected to the previous question where we don't keep track of this tactic state precisely. But having some kind of approximation of the real tactic state suffices for this purpose.
Hi, I first have a brief suggestion. So I would add a mode where one could at least add optionally the statement that this was produced by Aesop. Because if a proof breaks later on, then one knows, oh, I just have to remove it and run Aesop again, right? I mean, this is what we usually have in Isabelle. You see a Mattis line with a long list and you know, oh, this was Sledgehammer, right? And then you run it again. My question is actually, did you make timing experiments whether these scripts really are always faster? Because what I experienced in Isabelle is sometimes that you can switch between either getting a compact Mattis call or getting an explicit proof script with lots of details, etc. But then parsing this whole thing, because intermediate statements are written in ISA takes longer than running everything without parsing on the internal tactics.
Ah, interesting. So I did not do timings on this because I thought it was very, very likely the case that the produced script would almost always be faster. So my experience with the lean tactic system is that parsing the tactics is essentially free compared to the time that lean spends running the tactics, particularly when there are simplifier calls in there or something like that. These tend to take much longer than anything else that happens during tactic execution. So I would expect that it is possible that the explicit script is slower, but only in cases where all the tactics involved are so fast that we are basically talking like single millisecond range anyway. And in that case, it doesn't make a difference.
There was, I guess, a step that you, omitted, where like even you're reordering them, but it's still reordering into another straight line script, right? So at some point, this has to turn into a tree. Like, how does that work? Is that okay?
So see paper. It's a bit hard to describe because there's actually a multi-stage computation involved. But basically, we run over the script, we simulate the tactic state again, and that gives us the tree structure of the eventual script. And then there's a separate rendering pass that takes this tree structure and outputs the right combinators. So it's a whole other process.
Is that something that you can do without having to rerun the tactics?
Yes, this is fully static.
So I'm a cock user and not a lean user, but a very common sort of pattern that I find myself using is when sort of the second and the third and the fourth subgoals are more or less trivial, but it sort of does the unification of the meta variables that I want. So it's sort of apply this tactic, and then you have a semicolon and braces and say second and third and fourth subgoal, do these one-liners, and that makes, to my mind, more readable proofs because you can sort of get away with the simple one-liners and sort of continue with what is actually sort of the core of the proof. Is this something you do in Lean as well, or would this seems like it would sort of maybe muck up deliberate structure for readability?
So we are starting here with an initial Aesop proof, right? So at the start of it, at the very start, is this thing where we run Aesop and it solves the goal fully. So in some sense, we've already done the automation. And if you want this automated thing, then you can leave it at that. I think there is a case to be made actually for partial automation, where we don't generate the fully explicit script, but maybe we just run the more expensive things explicitly. And then once we have a goal that's very easy for Aesop to solve, we could insert Aesop calls in here. So then we get kind of the interesting steps explicitly and the not so interesting steps implicitly. I think this could be a nice idea.
Okay, let's thank the speaker.
Thank you.